Right, in this video we will look at locus of a complex number in a complex plane. So in a complex plane you have vertical axis which you use to represent the imaginary part of a complex number, and a real axis which is horizontal, and you will locate the real part of a complex number. So in general, you know that a complex number can be written in the form of a plus ib. So in this case, b is the imaginary part and a is the uh, real part. So if you were to locate this complex point, you can locate first the real part, which is a, and the imaginary part, which is b. So you would get this point, right? This is bi actually, uh, and this point we can name it as p of c, okay? Point of complex number c. So any point in the complex plane, it represent a complex number, a unique complex number. Okay, under this course you are supposed to learn about two types of locus, loci, which is you should be able to represent graphically a complex number. So z naught is a fixed point, it is usually given, and z is a variable complex number whose modulus of a difference, whose modulus of the difference between these two complex numbers. Now this is a fixed point, this is a complex point, variable point, is constant, right? The difference will also give you a complex number, obviously. So this will also give you a complex number, let's say w. So the modulus of the w is equal to r. So modulus of w is equal to r. So you are supposed to sketch the locus of z such that this modulus is equal to a constant. This is the first type, and the other type is argument of z minus z naught. Argument of z minus z naught is equal to some angle, right? Argument of c minus c naught is equal to some angle, right? These are two types of locus points. We will look at in detail what both of these types means. So let's say that instead of theta you can write 5/3, 5/6, or any point. So I think you get this. So we will look at two specific examples. So in general you are supposed to find the locus of such points, and as I said earlier, argument z minus z naught some theta, right? So in this special case, I'm gonna put z naught as 0, right? When I put z naught 0, which means it is centered, I will get, so let's say z minus z naught is equal to r. So let me put z naught equal to 0, then you will obtain z modulus of z is equal to r. So in this case, you have to find the locus of z such that its modulus is equal to r. Now here's the thing, you already know that complex numbers can be represented in two ways, in two forms. First form is a plus ib, which is the Cartesian form, and the other form is polar form. In the polar form, any point z can be represented by the distance between 0 and that point, right? Distance between 0 and that point. So if you only restrict yourself to the distance between these 2 points, there will be many choices, because let's say the distance is r. If you are to find any complex number whose r distance away from origin, you can find many choices. Let's say this is r, a point somewhere here is also uh, satisfying this criteria, somewhere here, somewhere here, somewhere. You can see that any point in this circle, any point in this circle would represent a complex number who is r distance away from origin, right? So there are infinite possibilities. So in order to avoid that, you have to also specify the direction. This is just like a vector, right? Just like a vector, you have a magnitude and you have to mention the direction. So direction is called the argument of a complex number, right? R is the modulus actually, right? Modulus, and theta is the argument of a complex number. Right, now you already know the answer to this. So basically you have to specify r and theta when you are looking at polar coordinates. Right, so if you are to find z such that whose modulus is equal to r, which means you have to find complex number such that its modulus is always r. So how many choices are there? There are infinite possibilities, infinite possibilities. So if you find a point here, yes, it will satisfy. And let's say this is r, r. So any point on this circle will have a distance between the origin which is equal to r. So any point in this C, any point on this circle will satisfy this equation. Now you have obtained the locus of z. So locus is the path that z takes, which means this any complex point which falls upon this circle will satisfy this equation. It will satisfy this equation. You can see here that this will give you a circle. Let's see if we can figure this out using Cartesian coordinates. You know that the characteristic equation of a circle already. So let's say z is given by x plus iv. So z modulus of z is called x squared plus y squared square root, right? Square root of x squared plus y squared. So this is equal to r. Now if I get rid of the square root, you will get x squared plus y squared equals r squared, and x squared plus y squared minus r squared is equal to 0. Okay. Now we already know that this characteristic equation represents a circle which is centered at the origin and has a radius r. Okay, see, so in both cases we get the same thing. So you can show this by analytically, or you can either show it by graphically. Okay, right. So in this case you can see here that if I select a point somewhere here, let's say p1, sorry, point of z1, it has a distance r, but the argument will be theta1. So if I select a point somewhere here, z2, it has a radius r, but there will be minus, let's say minus alpha. The argument is different. Point somewhere here, the modulus is the same, but the angle is different. Let's call it gamma. So if you are asked to find the locus of the point such that the argument, what is the argument? Argument is the angle the complex number makes with the positive x-axis, right, over the real axis. So if you are supposed to find argument of c such that this is equal to a constant, So you should find all the complex numbers whose argument is theta, right? So how do you go about finding it? For the sake, let's take an example. Let's say this is 5 by 3. So argument 5 by 3, 5 by 3 means 60 degrees. So you have to find any z, doesn't matter what the modulus is. The only requirement is being the argument has to be is equal to 60 degrees, right? So I have chosen 4 points here. On all the 4 points, you can see that the 4 points have different arguments. This theta 1, theta 2, theta 3, theta 4, right? So the arguments differs. So you have to find C such that the argument is 60 degrees. So we'll look at one option being, let's say I find Z such that angle is 60 degrees, right? Also I can find a point on this line. So on this line Z1, let's say Z2, this complex number also has an argument of 60. What about another point? This one will also have an argument of 60. So you can see here, you can deduce that any point on this line, any complex point on this line will satisfy this requirement. So this is the locus of Z. This is the locus of C which satisfy this equation, right? So in the next video we will look at more general cases.